So anything we can do to help you out is something I believe worthwhile. Okay, punks. It's Torricelli time. Torricelli, I spelled your name wrong again. Okay, Torricelli. Basic idea. Starts with the water tower. Whoosh, whoosh, foomp, foomp. You put a tiny hole in that water tower. Okay? Now, if you know anything about Hole in the Bucket songs with Goofy and Liza from your childhood, then you and I have lived the same childhood. But if this water tower is filled up to some height with water or some other, fluid, we'll say there's not a stickiness, viscous issue we're worrying about, then with the hole in the bottom, the water will go whoosh, and it will come out at some velocity. Now, could we figure out what velocity the water comes out with? Sure. Very simple to do. We use the same thing as we always do. Pull out big old Bernoulli. Give me the burn. One thing we can note, though, this is an interesting point, is that the pressure up here pushing down on the water, we'll call that P1. That is the same exact pressure that is pushing in here, because it's just the atmosphere, and pressure it's a scalar, it has no direction, so it can push down and sideways. So these are equal. So we have our big old Bernoulli equation, which is P1 plus rho Gy1 plus 1/2 rho V1 squared equals rho P2 plus rho Gy2 plus 1/2 rho V2 squared. Whew, using that a lot. Because those two P's are equal, whoosh, whoosh, they're going to subtract away from each other. Who cares? Okay. The other thing that Torricelli assumes, and this is Torricelli's assumption here, this is kind of a given for us, we can think about it, or we can say that they're generally equal. Technically, you could make the argument like, oh, Mr. Botzer, that's a 20-foot high water tower, and the column of air has some pressure gradient to it. But nobody cares about a 20-foot pressure gradient through something with a density of 1.2 kilogram per meter squared. Who cares? So they basically go away. What we can do with this, if we look at everything here that's left over, is everything has a rho in it, and rho is a density. It is a mass per unit volume of an object. So what we can kind of quickly do, if just everything's left over with rho, is we divide out the rho's. All the rho's divide out. That was nice and friendly for us. And if we start looking at stuff now, the other thing that Torricelli assumes in this kind of water tower scenario is he assumes that the top of this water tower or bucket is so much larger than the tiny little pinpoint hole at the bottom that as this water goes shooting out of the hole here, this water up here, this velocity V1, it's 0. It's not really moving. Yes, technically it is slowly going down. If you wait long enough, it will empty. But for a brief instant of time, nah, who cares? Technically we care. This is our related rate slab. But Torricelli doesn't really care about that. He says this initial velocity here is 0. And because of this, that goes away. So the only thing we're left with in Bernoulli's equation right now, because those initial pressures, P1 and P2 are the same, and the initial velocity, V1, of the water dropping is 0, or it's negligible in this problem, is we are just left with Gy1 equals Gy2 plus 1/2 V2 squared. Okay? And if we kind of look at this, we're like kind of done here. y1 and y2 signify the height of the water. So if we took these like terms here and put them together, what we could do with this is we could say that g times y1 minus y2, brought the terms together, I brought y2 over to the left side of the problem here. Y1 and y2 could be considered, or y1 minus y2 could just be considered the change in height of this system. Okay, that's just a delta y. So what we have here is g in delta y, the depth of the system, equals 1/2 v2 squared. At this point, we're like done here if this is v2. We can just say that v2 equals 2g delta y, and then there's a square root here. And I personally like writing my square roots with fractional exponents. But that right there, this equation, this Bernoulli's equation that's been transformed with some basic assumptions into Torricelli's, actually gives us the exit velocity speed of water being shot at a hole. It's just root 2g and then the depth of the water, delta y or delta h, or whatever depth of the water of the pool you have is. So that's kind of a cool thing there, that you can just quickly get with Bernoulli's equation and kind of work from that. Now, like I said, this does change a bit if you are looking for, what does happen here if this velocity isn't 0. What happens to this value? How does it change with time as that drops? Because you have to imagine that as this water is dropping down, our delta y here isn't the same. Our depth of the pool is actually shrinking. And if it's shrinking, that means the velocity isn't moving as fast. The ejected water is slowing down. So we kind of get an interesting scenario there that we can investigate using a little bit of calculus if we're curious about that. But that's what we're doing in our lab in class. For right now, this is just Torricelli's theorem. It's just using Bernoulli's equation, big ol' burn, crossing out densities, initial velocity 0, and then working out the math to solve V2. So with that, that is Torricelli, who I can never spell right. Sorry about that. So, Finn. Okay. That was the last thing I wanted to do for that. I wanted to get a Torricelli in there.